Hey, good morning, everybody. First of all, I would like to say that I'm not professor. Yeah, I'm just researcher. So our team includes three members. We are Professor Kyoon-Ho, Professor Jong-Sung Kim, and me, Professor Van-Thanh Pham. And we work at Department of Quantum Nuclear Engineering, Section University, Korea. So the title of our research is Nano modeling of the single crystal copper using the strain gradient crystal plasticity theory and optimization algorithm. And this is the table content. We will go to the first section in introduction. As you know, the motivation of our study certainly is the copper material with the high activity has attracted quite attention in several mechanical fields. And the crystal plasticity finite element modeling, CPFEM, of nano indentation test is a powerful tool to study microscopic deformation. And you can see in the left figure, this is the copper material, and the right figure is the nano indentation test. And the accuracy of the CPFEM significantly depends on the selecting of the parameter we use in modeling. And currently, multi-existing methods carry the larger error due to the inadequate parameter determination. So a new method is studied to address this problem. And our objective is developing a new and effective method for modeling the nanodetection using the strain gradient crystal plasticity theory and Harvey-Hawk optimization algorithm. And we go to the section 2, the methodology, the strain gradient crystal plasticity theory. And we already know that the solid material with anatomy and orderly arrangement, you can see in the left figure. And the crystal structure in copper material is FCC, phase centered cubic unit cell, you can see in the right figure. And the plastic deformation ability of solid material undergoes the permanent deformation, and you can see in the picture. Okay. Oh, sorry. Okay. And the deformation gradient F is decomposed into two parts, elastic and plastic part. And we can see in the equation, and Fe is elastic. We can calculate it based on the general Hooke's law. And Fp, plastic part, we can calculate. And with the plastic velocity gradient, we can use this equation. And this equation we should make attention to for the shear rate, which is the power law calculating the equation. In this equation, T tau C alpha is resistant on slip system alpha, and tau alpha is the soft shear stress on the system alpha. Okay. Also, we will use the ball hardening model to solve this model. As the initial moment t equals 0, when plastic deform occurs, we will calculate the tau C alpha using the equation, in which the insist resistance tau C0 and SSD means the statically solid dislocation, and GND is the symmetrically necessary dislocation. Okay, with the plastic deform, we calculate, we model the evolution of resistance using this equation. And as you can see here, there are many parameters we need to determine to get the accuracy modeling. And in our study, to model the FCC single crystal plasticity, the UMass subroutine have been developed to use in the Abaca program. Okay, and we go to the Harvey-Hawk optimization. This algorithm is a meta-holistic optimization algorithm inspired by the hunting behavior of Harvey-Hawk in the nature. You can see in the left figure. And this algorithm includes three phases. The first phase is the exploration, and the second is the transition from exploration to the exploitation, and the last is the exploitation. Due to its efficiency, the SSO algorithm is employed to calibrate the simulation parameter in this study. Okay, and section 3 is the proposed methods of indentation modeling. In this study, we used the non-indentation experiment conducted by Uchaki and Zazabel in 2014, and this is their results, the indentation depth force relationship. And in the below figure, you can see the simulation model with Berkovic intended, and this is the mesh of the computational domain. You can see here. And the objective of our study to minimize the difference between the simulation and experiment model. Experiment, this is we using the equation. Yeah, and this is the process of performance. Firstly, we will selection. We select a productive parameter from H1 to Hn and define the ranges of modeling critical plasticity and define the number of iteration and SSO parameter. And we will increase the iteration, and in each iteration, the SSO will generate a new solution, and we will update the selected parameter, and we analyze the FE model. And then we will check the object's function. And if the composition is satisfied, the process will be end. And this is the result and constant result assessment. You can see in the top table 1, we seek basic constitutive parameter of the copper yield for modeling. And in this study, we will consider 6 parameters here with their rate here. And the initial value we use based on the reference study here. And this is the results. And you can see here, the convergence of the objective function is 30 iteration. With SSO, we choose the number of half is 5. And all parameters become constant up to only 12 iterations. You can see here, after 12 iterations, all parameters be constant. The change of 6 constitutive parameter you can see in this figure. And if we can see that in the dislocation change coefficient and the institute's lattice resistance is the highest change among 6 parameters, and hardening exponent and initial density of SED have small changes. And you can see in the left figure, this is the FS curve obtained from the proposed methods. Before the updating, you can see that significantly differ from the experiment and the experiment data and the simulation. The experiment in the blue curve and before updating in the red curve. And after we update the model, and you can see the better result we can get with only the differ only around 5%. And you can see in the table 2, all updated value are in their predefined range. It shows that the constitutive parameters have been successfully selected using the proposed methods. Okay, and here is the simulated displacement result of copper after loading and unloading stages. We can see that the maximum displacement decrease about 3% from the initial value, which indicate that the high strain hardening behavior of copper. And we also see that the singing behavior here, you can see here, is a common observed in the material with high strain hardening behavior. And then this is the simulated shear stress result of copper after loading and unloading stages. The distribution of shear stress near the indentation point is a form of butterfly, you can see here. And it can effectively reflect the inosotropic nature of plastic flow in a single crystal copper. So then we go to the conclusion session. We have 4 conclusions. First one is the UMass subroutine is effectively developed by using the series SDCP theory. And the second one is the SSO algorithm is successfully employed to create the simulation parameter. And the third one is the effective or the proposed method it demonstrates through the comparison between the simulation and the experiment results. And the last one is the discussion with you. Reasonable results, suggesting that the copper material inhibits the high strain hardening behavior and an inosophic nature of plastic flow is a single crystal form. Okay. And this is some reference of this study. Okay, right now I would like to thank you for the attention. Thank you.